The last star in the universe may not be a giant, a blue firestorm, or anything visible in the night sky. It may be a tiny red dwarf, burning so softly that human eyes could never see it, yet lasting long after stars like the sun have faded into silence. These faint suns are everywhere, hiding in plain darkness, carrying planets, danger, hope, and perhaps the final warm shelters of cosmic time. Thank you for spending part of your day or night with this journey. If this kind of calm space storytelling brings wonder to your quiet hours, a like, a subscription, or sharing it with someone who loves the universe helps this channel keep going. And before the story deepens, leave a comment with where you're listening from and what time it is there. Now, let the red light of the smallest stars guide the way into the long future of the cosmos. In the quiet inventory of the cosmos, the stars that matter most are often the least visible. They do not blaze blue in young clusters. They do not swell into red giants bright enough to reshape the sky. And they do not end their lives in explosions that scatter heavy elements across space. Most of them are small, cool, dim, and easy to miss. They are red dwarfs, the faint stars that fill the galaxy in enormous numbers while hiding almost completely from unaided human sight. No red dwarf shines brightly enough to stand out in Earth's night sky without help. The human eye looks upward and sees familiar points of white, yellow, orange, and blue light. But the most common kind of star in the universe remains largely absent from that view. It is there in the background, surrounding the solar neighborhood, filling the spiral arms of the Milky Way, and likely outnumbering sun-like stars by a wide margin. Its mystery begins not with rarity, but with invisibility. A red dwarf is not red in the dramatic sense of a burning coal or a sunset cloud. It is red because it is cool by stellar standards, giving off more of its light at longer wavelengths than hotter stars do. Its surface is far cooler than the surface of the sun, and its light is weak enough that even nearby examples can seem like ghosts beside brighter stars. Yet this dimness is not a sign of failure. It is the outward mark of extreme patience. A red dwarf spends its fuel with extraordinary care, turning hydrogen into helium at such a slow pace that its lifetime can stretch far beyond the present age of the universe. The sun is already middle-aged, with a finite future measured in billions of years. A small red dwarf can last for trillions of years, quietly shining through ages so vast that ordinary ideas of cosmic history begin to feel too small. In that sense, the most modest stars may also be the most enduring. The first surprise is their number. Most stars in the Milky Way are believed to be red dwarfs, and the same is expected across the wider universe. They make up the quiet majority of stellar objects, not because they dominate any single sky with brilliance, but because nature appears to make small stars more easily than large ones. A massive star requires a huge amount of gas to gather in one collapsing cloud, and once it begins to burn, it consumes its fuel with fierce speed. A red dwarf forms from a much smaller share of material. It is economical from the beginning, born with less mass, less brightness, and a far longer future. The galaxy is therefore not mainly a place of stars like the sun. It is mainly a place of dim red embers, scattered by the billions, slowly burning in the dark. Their faintness creates a strange imbalance between what exists and what is seen. Astronomy begins, for ancient human cultures, with bright stars. The visible sky becomes a map of luminous exceptions. Constellations are drawn from the stars bright enough to mark patterns, and those stars are usually larger, hotter, or closer than the hidden majority. Red dwarfs are present, but they do not announce themselves. Only with telescopes, careful surveys, and measurements of motion and brightness does their population come into focus. In the Sun's own neighbourhood, many of the nearer stars are red dwarfs. They sit close in cosmic terms, yet most are too dim for ordinary vision. The universe is not hiding them deliberately, but their nature makes them secretive. Their light is real, their gravity is real, and their influence on nearby planets may be profound. Yet they live below the threshold of casual seeing. That threshold matters because red dwarfs may be central to several of the largest questions in science. They are tied to the search for planets beyond the solar system, to the possibility of life around other stars, and to the far future of habitability when brighter stars have aged and died. Around a star like the Sun, the zone where liquid water can exist on a planet's surface lies at a comfortable distance, wide enough for Earth to orbit with room between intense heat and deep freeze. Around a red dwarf, the same zone lies much closer in, because the star gives off so little energy. A planet must draw near to receive enough warmth. This closeness creates danger and possibility together. The star is small and long-lived, offering stability across immense time, but a nearby planet may face tidal locking, atmospheric erosion, powerful flares, and strong gravitational forces. The red dwarf is therefore not a simple refuge. It is a difficult promise. It may hold habitable worlds in great numbers, yet those worlds must survive conditions unlike Earth's familiar arrangement with the Sun. The idea becomes more compelling because time is on the side of these stars. Life on Earth requires long continuity. It appears early in the planet's history, then slowly changes the atmosphere, the oceans, and the surface. Complex life takes far longer to become visible in the fossil record, and technological civilization appears only in the most recent instant of Earth's story. A short-lived star gives planets less time to develop such complexity. A red dwarf, by contrast, can offer an enormous duration, provided its activity does not sterilize or strip nearby worlds. If a planet can keep an atmosphere, maintain liquid water, and avoid being reduced to a scorched or frozen wasteland, then a red dwarf may provide a stage that lasts almost inconceivably long. Not merely longer than human history, not merely longer than Earth's history, but longer than the lives of stars like the Sun by hundreds or thousands of times. This is why the smallest stars can carry such large meaning. Their lives extend into an era the universe has not yet reached. The present cosmos is still young compared with the possible lifetimes of many red dwarfs, since the universe is only about 13.8 billion years old. Even the oldest red dwarfs have barely begun their evolution. None has yet reached the end of its natural stellar life. Every red dwarf visible to modern astronomy, from the nearest dim neighbour to the most distant detectable population, is still in an early phase. A universe filled with ancient galaxies still contains red dwarfs that are, in their own slow way, infants. This reverses the usual feeling of age in astronomy. Galaxies can seem impossibly old. Clusters can contain stars born near the beginning of cosmic history, and white dwarfs can cool for billions of years. But red dwarfs make even those spans seem brief. Their future is longer than the universe's past. A star can be small enough to escape notice and still be built for endurance on a scale that changes the meaning of time. Their hidden importance also reaches toward the far future of humanity, or any intelligence that survives long enough to think beyond its original star. The Sun will not remain gentle forever. As it ages, its brightness increases, and Earth's long habitability is temporary. Long before the Sun becomes a red giant, complex life on Earth may face conditions too warm and unstable to endure. A civilization that seeks continuity across cosmic time would eventually have to look outward, toward other stars and other systems. red dwarfs would be unavoidable in that search because they are numerous, long-lived, and often accompanied by planets. Some may be too violent in youth, some may flare too often, some planets may lose their air, their water, or their chance for surface life. Yet among such vast numbers, even rare success could matter. A small fraction of habitable red dwarf systems would still mean an enormous population of possible refugees, laboratories, and living worlds across the galaxy. The same feature that makes red dwarfs hard to see also makes them useful for planet discovery. Because these stars are small, a planet passing in front of one can block a more noticeable fraction of its light than the same planet crossing a larger star. Because their habitable zones lie close in, planets there orbit quickly, producing repeated signals for telescopes to measure. Modern exoplanet science therefore pays close attention to red dwarfs, not because they are gentle by default, but because they are common and revealing. They give astronomers a practical way to find small worlds and study their possible atmospheres. In the faint light of a red dwarf, the shadow of a planet can become easier to detect. From that shadow, science begins to ask whether the planet has air, whether it holds heat, whether its chemistry hints at stability, and whether its surface could ever support life. The faint star becomes a doorway into one of the deepest uncertainties in the cosmos. Still, the red dwarf story is not only about planets, life, or future homes. It is also about the final architecture of starlight itself. Massive stars live fast and die young. Sun-like stars glow for billions of years, then swell, shed outer layers, and leave behind dense remnants. Red dwarfs endure after these brighter families have faded. In the distant future, when star formation slows and the supply of fresh gas runs thin, red dwarfs may remain as the last ordinary stars still shining. Their glow may be weak, but weakness can last. Across trillions of years, the universe may become increasingly dark, populated by remnants, cooled worlds, and the fading products of earlier stellar generations. In that long twilight, red dwarfs stand as the final candles of normal fusion, the last places where hydrogen still becomes helium in the heart of a star. They are not spectacular in the present sky, but their destiny may be spectacular in silence. They may outlive nearly everything that currently defines the visible universe. This is the first great paradox of red dwarfs. They are the smallest true stars, yet they may become the longest-lived lights. They are the most common, yet almost unseen. They are cool and dim, yet they may warm planets for spans of time that dwarf the life of the sun. They may threaten nearby worlds with flares and tidal forces, yet they may also offer the most abundant settings for life beyond the solar system. They are ordinary in number and extraordinary in consequence. A red dwarf does not demand attention the way a supernova does. It does not carve a bright shape into a nebula or dominate a constellation. It simply persists. It burns quietly, mixes its fuel, guards its energy, and waits through ages. In that waiting lies its power. The universe may not end in sudden darkness, but in a long decline where the brightest stars disappear first and the faintest remain. Red dwarfs, nearly invisible now, may become the final witnesses to cosmic time, carrying the last steady glow into an era beyond stars like the sun. Their story begins in darkness, because darkness is where they have always been most at home. The universe does not reveal its true population at a glance. A bright sky gives the impression that stars are mostly grand things. White and blue suns burning with confident force, yellow stars like the sun, and orange giants shining across enormous distances. Yet this is a selection effect, a trick created by brightness. The The stars most easily seen are not the stars most commonly made. They are the loudest members of a much larger family. Beneath them, filling the galaxy in numbers too large for ordinary vision to suggest, are red dwarfs, the quiet majority of the stellar world. Their dominance is not obvious because they are small, cool, and faint. A red dwarf can sit close to the solar system and still remain invisible to the unaided eye, while a rarer luminous star can be seen from far across the galaxy. The night sky is therefore not a fair census. It is a gallery of exceptions, a map drawn by light rather than abundance. And the missing population changes the meaning of what a galaxy is. It is a vast system in which most stars are dim red points, each burning gently, each adding quietly to the mass and structure of the galaxy. Their faintness gives them an almost hidden role. They do not define the constellations. They do not appear in the ancient names that attach human memory to the sky. For most of human history, their existence is unknown, not because they are far away, but because their light is too weak to cross the small distance between reality and perception. This creates one of astronomy's humbling lessons. The visible universe is not the whole universe, and even the visible sky can mislead by showing the brightest objects as if they were the most important ones. Red dwarfs correct that impression. They are ordinary in the deepest statistical sense, yet their ordinary nature is almost completely hidden. When astronomy begins to measure stars rather than simply admire them, this quiet population starts to emerge. Nearby stars can be tracked by their slow motion against the background, by their faint glow on photographic plates, and later by precise surveys that compare brightness, colour, distance, and motion. The more carefully the neighbourhood around the Sun is counted, the more red dwarfs appear. This is how the galaxy grows stranger. The nearest stellar neighbours are not all brilliant suns. Many are dim red dwarfs, modest objects with only a fraction of the Sun's mass. Others move alone through space, faint and steady. They are close in cosmic terms, yet they remain visually hidden. So the local galaxy becomes a place where nearness and darkness overlap in ways that ordinary sight cannot untangle. Their presence shows that distance is not the only reason a star is hard to see. A star can be almost next door and still belong to the dark background of human awareness. The reason red dwarfs are so common lies in the way stars are born. Stars form inside cold clouds of gas and dust, where gravity gathers material into dense knots. If enough mass collects and pressure rises high enough, the center becomes hot enough for hydrogen fusion, the process that makes a true star. Nature does not make all stellar masses equally often. Small stars form more readily than massive stars because it is easier for smaller pockets of material to collapse into stable objects. The larger stars are rare, short-lived, and demanding. They require great reserves of gas, and once formed, they burn their fuel with extreme intensity. Red dwarfs require far less material and settle into a slow, stable pattern. This means that, over the history of a galaxy, many more low-mass stars are produced than high-mass stars. The result is a cosmic landscape in which the most common stars are not the brightest flames, but the smallest sustainable ones. Their abundance also means that red dwarfs affect the galaxy even when they cannot be easily seen. Each one has gravity, each one contributes mass, each one may host planets, dust, asteroids, or icy bodies. Together, they make up a major part of the stellar population that shapes local neighborhoods and long-term galactic evolution. A single red dwarf is easy to ignore beside a bright giant. Billions of them are not. They are part of the galaxy's hidden architecture, a dim foundation beneath the bright features that telescopes first notice. This quiet majority also changes the way life is considered in the cosmos. If planets are common around red dwarfs, then the most common planetary environments in the galaxy may not resemble Earth's relationship with the Sun. Instead, Many worlds may orbit small, cool stars, circling close in a reddish twilight. The search for life, therefore, cannot focus only on sun-like systems. The galaxy's most frequent setting for rocky planets may be around red dwarfs, which means the question of habitability is tied to a kind of star that was once nearly invisible to human thought. A hidden majority of stars may imply a hidden majority of worlds. The statistical weight of red dwarfs becomes even more striking when placed against cosmic time. Massive stars live briefly, sometimes only a few million years, and then end in violent transformations. Sun-like stars survive much longer, but even they have limited lives measured in billions of years. Red dwarfs, by contrast, can remain stable for spans that reach far beyond the present cosmic era. A galaxy that appears bright today may slowly become a galaxy whose living stars are mostly red dwarfs. The stellar population of the far future is already quietly present. It is made of the objects that barely shine in the current sky, the ones patient enough to outlast the brighter families around them. There is a deep contrast between visibility and destiny. The stars that dominate the eye may not dominate the future. A blue giant can flood space with light, sculpt its surroundings, and die before a small red dwarf has meaningfully changed. A yellow star can nurture a planet for billions of years, then leave the main part of its life behind. A red dwarf begins faint, stays faint, and persists. Its story is not dramatic by the standards of human attention, but it is decisive by the standards of cosmic duration. The universe rewards endurance in a way that the eye does not. Over immense time, the spectacle fades, while the quiet majority remains. That makes red dwarfs central to the future habitability of the universe. They may be the last places where planets receive steady warmth from fusion. They may host the last biospheres, if life arises or survives there. They may become the final beacons for any intelligence that moves from star to star, seeking systems where time still remains. Their smallness is not a limitation in that distant age. It is the reason they are still present. Even the nearest red dwarfs carry this double meaning. They are both local and cosmic, both faint neighbours and signs of the universe's long-term direction. Studying them is not merely a search for small stars. It is an attempt to understand the most typical kind of stellar environment, the most durable kind of ordinary light, and perhaps the most common kind of planetary system. As telescopes improve, red dwarfs shift from background objects into central subjects. Their planets become targets for atmospheric studies. Their flares become clues to magnetic activity. Their slow burning becomes a window into futures that no red dwarf has yet reached. They are test cases for how life might persist around small suns, and how the galaxy may look when its brightest eras are over. The quiet majority remains quiet, but it is no longer meaningless. It suggests that the universe is built less around brilliance than persistence. The sky that seems full of bright stars is, in truth, supported by countless faint ones. The Milky Way glows because of its luminous members, but it endures through its dim ones. Red dwarfs do not ask for attention. They gather in the margins of sight, burn slowly, and carry the future in their weak red light. Their abundance turns darkness into something more complex. Empty-looking space is not empty. Faintness is not absence. The unseen can be the common, and the common can be the foundation on which the longest chapters of cosmic history are written. In the census of stars, the universe speaks softly, and most often it speaks in red. A red dwarf survives because it is careful with fire. In the deep interior of every true star, matter is pressed until heat and pressure become intense enough for hydrogen nuclei to fuse into helium. This is the central engine of starlight, It is not burning in the ordinary chemical sense, where fuel meets oxygen and releases heat. It is a nuclear process, a transformation of the smallest and simplest atoms into heavier ones, with a tiny part of their mass converted into energy. In a star like the Sun, this energy slowly moves outward until it leaves the surface as light and heat. In a red dwarf, the same basic process occurs, but at a gentler pace. The star has less mass pressing down on its center, so its core is cooler and less intense than the core of a larger star. Fusion still happens, but it happens slowly. The result is a star that glows faintly rather than brilliantly, conserving its hydrogen across ages that can exceed the lifetime of the Sun by an almost unimaginable margin. The secret is not only that the red dwarf begins with less fuel, it is that it spends that fuel in a very different way. A massive star lives like a furnace with too much draft, driving fusion rapidly because gravity crushes its core with enormous force. It can shine with spectacular power, but that power is expensive. The brighter a star burns, the faster it empties its central supply. The Sun is far calmer than a massive blue star, yet even the Sun uses hydrogen mostly in its core, while helium, the ash of fusion, gradually builds there. Over time, the Sun's core changes. The fuel available for stable hydrogen fusion declines in the central region, and the star must slowly adjust. A red dwarf takes another path. Its small mass makes its interior behave in a way that keeps the whole star mixed. Hot material rises, cooler material sinks, and the gases circulate through much of the star in a process called convection. This means hydrogen does not sit unused in the outer layers while the core ages alone. Instead, fresh fuel can be carried inward, and helium can be carried away from the center. The star becomes a slow-turning reservoir rather than a core surrounded by inaccessible supplies. This mixing gives many red dwarfs a remarkable advantage. They can use a much larger fraction of their hydrogen than stars like the Sun can. A Sun-like star does not consume all its hydrogen before leaving its steady main phase. Much of that hydrogen remains outside the core, still present but not available in the same direct way for the fusion that holds the star in balance. A fully convective red dwarf is different. Its interior is stirred so thoroughly that the separation between core and outer layers becomes less strict. The fuel supply is shared. Helium does not simply pile up in the middle as quickly, and hydrogen keeps finding its way into the region where fusion can continue. The red dwarf therefore avoids the rapid central aging that marks larger stars. It remains modest, slow, and steady. Not because it is inactive, but because its internal structure allows it to ration energy with extraordinary efficiency. This is why smallness becomes endurance. Gravity is weaker than in larger stars, so the fusion rate remains low. The surface is cooler, so the light output is dim. The mixed interior makes fuel last. Together, these features turn a low-mass star into one of the longest-lived objects that can still shine by ordinary stellar fusion. The relationship between mass and lifetime can seem backward at first. A star with more material appears to have more fuel, so it might seem natural for it to live longer. But stars do not behave like simple lamps filled with oil. Adding mass increases pressure and temperature at the center, and that makes fusion run faster. A star twice as massive as the Sun does not merely burn twice as brightly, it can burn many times more fiercely and exhaust its central fuel much sooner. The smallest red dwarfs, by contrast, have only a small fraction of the Sun's mass, yet their energy output is so low that their fuel supply can last for trillions of years. They are not rich in fuel compared with the larger stars. They are frugal beyond comparison. Their faint light is the evidence of that thrift. Every moment, a red dwarf releases far less energy into space than the Sun does, but it does so with a patience no bright star can match. The surface of a red dwarf reflects this inner restraint. It is cooler than the sun's surface, so its light leans toward red and infrared wavelengths, the slower, longer waves of electromagnetic radiation. Much of its energy emerges beyond the range most sensitive to human eyes. This is one reason red dwarfs vanish from ordinary sight even when they are nearby. They are not only dim in total light, they also shine in a way that makes them visually understated. To instruments, however, their signal is clear. They are real stars, sustained by hydrogen fusion, balanced by the struggle between inward gravity and outward pressure. Gravity tries to compress the star. Fusion provides energy that heats the gas and supports it against collapse. In this balance, the red dwarf finds stability. It is not on the edge of death, it is on the edge of patience. There is another quiet consequence of their slow fusion. Red dwarfs change so gradually that human timescales cannot easily register their evolution. A bright star can alter its surroundings, shed material, and race through life stages in spans that are short by cosmic standards. A red dwarf spends vast periods doing almost the same thing it did before. Its brightness may vary because of magnetic activity, star spots, and flares, but its deep nuclear evolution is extremely slow. The core does not rush toward exhaustion. The structure does not rapidly reorganize. Its long life is not a series of dramatic chapters, but a sustained state of controlled transformation. Hydrogen becomes helium atom by atom, and the star carries that change through itself like a slowly mixed tide. This makes red dwarfs difficult to describe in the usual language of stellar drama. Their most important feature is not spectacle, but duration. Yet duration can be its own form of strangeness. A small red dwarf that forms early in the history of the Milky Way may still be almost untouched by age today. It has burned since before the sun existed, through the formation of countless planets, through extinctions and the rise of intelligence on at least one world, and still it has consumed only a small portion of what it can use. Its light, weak as it is, represents a clock that runs slowly enough to outlast familiar cosmic landmarks. The star does not need to be bright to be profound. It only needs to continue. This deep steadiness has meaning for planets, though the details are complicated. A planet around a red dwarf receives enough warmth only if it orbits close, and that closeness can bring strong radiation, tides, and atmospheric loss. The same slow engine that makes a red dwarf faint can provide time, while the active surface may threaten the very air a world needs. This tension remains central to the red dwarf mystery. Still, the nuclear story remains astonishing. The universe begins with hydrogen as its most abundant ordinary element, and red dwarfs are among the most patient machines for turning that hydrogen into helium and light. They do not waste their inheritance. They do not rush toward brilliance. They keep their interiors stirred, their cores supplied, and their luminosity low. A star like the sun lives long enough to shape a planetary system and give life a chance. But a red dwarf can extend that chance across spans the current universe has not yet tested. Every red dwarf now shining is still young compared with its possible future. Its hydrogen supply is not near exhaustion. Its final stages remain theoretical because no example has had time to reach them. In the present cosmos, red dwarfs are not elderly remnants. They are quiet engines near the beginning of a life that may continue after the brighter sky has changed beyond recognition. This is the hidden power of the smallest stars. They do not conquer darkness with brilliance. They negotiate with it, giving off enough light to remain stars, enough warmth to matter, and little enough energy to endure. Their fusion is slow, their interiors are stirred, and their future is vast. Inside them, The simplest atoms are being rewritten into helium with a patience that turns faintness into survival. The red dwarf burns, but it does not hurry. In that refusal to hurry, it becomes one of the universe's most durable forms of light. The old universe is already filled with relics, yet the red dwarfs inside it are still young. The first stars have come and gone. Massive stars have burned, collapsed, exploded, and seeded space with heavier elements. Planets have formed from enriched dust. Galaxies have collided and settled into new shapes. Earth has passed from molten beginnings to oceans, continents, life, forests, animals, and intelligence. Against the human sense of time, the cosmos seems ancient beyond reach. But to a red dwarf, the universe itself is not old. It is not even middle-aged. It is closer to a morning that has barely begun. The present age of the universe, about 13.8 billion years, is immense beside human history and brief beside the lifetime of a small red dwarf. A star like the Sun can change meaningfully across that span. A massive star can live and die many times within it. But the smallest red dwarfs can keep shining for trillions of years, so long that no example has yet had enough time to reveal its final chapters. Every red dwarf that exists today, even one born near the earliest periods when stars could form, remains in the long, stable phase of its life. None has become old in the way stellar evolution predicts it eventually will. None has yet run through the slow transformation that turns theory into observation. This makes red dwarfs scientifically familiar and deeply unknown at the same time. Their present behavior can be studied directly. Their masses, temperatures, brightness, magnetic activity, and planetary systems can be measured. But the distant future has to be inferred from physics rather than seen in the sky. Astronomy is often a science of looking backward, because light takes time to cross space. A telescope can view a galaxy as it was billions of years ago, catching ancient light from a younger universe. Yet even this power cannot show an elderly red dwarf, because the universe has not produced one. No matter how far a telescope looks, it looks into a universe too young for the final age of these stars. The evidence is not hidden by distance. It is absent because time has not yet supplied it. This is a rare kind of limit. In many areas of astronomy, some object somewhere has already reached an extreme state. There are newborn stars, dying giants, supernova remnants, neutron stars, black holes, white dwarfs, and early galaxies. Red dwarfs refuse this completeness. Their life cycle extends beyond the current cosmic archive. They force science to describe a future that no eye can confirm. Models can follow how hydrogen is consumed, how internal mixing continues, how brightness gradually changes, and how the star may evolve when its fuel is finally depleted. But these models describe an era farther away than the entire history of stars so far. The red dwarf becomes a time machine pointed forward, not because it travels into the future, but because its ordinary existence implies a future longer than the universe has already lived. This alters the emotional scale of cosmic history. The Big Bang marks the beginning of the hot, dense state from which the observable universe expands. The first atoms form, the first stars ignite, the first galaxies gather, and the long structure of matter begins to emerge. These events can feel impossibly remote, yet red dwarfs make them part of a prologue. If a small red dwarf can shine for several trillion years, then the current age of stars is only the opening chapter of a much longer stellar era. The universe has had time to make bright structures, life-bearing planets, and complicated chemistry, but it has not had time to age its smallest suns. A red dwarf born near the beginning may have passed through cosmic storms, galactic mergers, and countless changes in its surroundings. While remaining almost the same in its deep interior, its surface may flare. Its planets may migrate or erode, its neighborhood may change. But the star's nuclear clock moves with a slowness that makes almost everything else seem temporary. The reason lies again in the connection between mass and pace. In a low-mass red dwarf, gravity squeezes the center gently enough that fusion proceeds slowly. The fully mixed interior keeps hydrogen available across much of the star. The light output remains low. All of this spreads the star's available energy over a vast duration. It is not simply that a red dwarf has a long youth. Its stable adulthood is so long that youth and maturity blur together from the viewpoint of the present universe. There has not been enough time for a red dwarf to show the aging signs expected near the end of its main sequence life, the long phase during which hydrogen fusion supplies its energy. This creates an odd mismatch between theory and observation. For larger stars, many stages can be studied because the universe is old enough for examples to exist. For red dwarfs, the future stages are known mainly through physical reasoning. The laws of stellar structure can be applied, but the sky contains no completed sample. Even the term old becomes slippery. A red dwarf that formed more than 10 billion years ago is ancient in relation to Earth and the Sun, yet young in relation to itself. It may have existed before the solar system formed, before Earth cooled, before the first living cells left chemical traces, before oxygen reshaped the atmosphere, and before animals moved through ancient seas. It may still have most of its workable hydrogen. It may continue after the sun has expanded and shed its outer layers, after Earth has changed beyond recognition, and after countless brighter stars have ended. The red dwarf holds a kind of private timescale, connected to the universe but not hurried by it. Its age cannot be understood only by counting years already past. It must also be understood by the years still left. That remaining future is almost incomprehensible. 1 trillion years is a span long enough for galaxies to change their brightness, for star formation to decline, and for the universe's night to become much quieter. Red dwarfs carry starlight into that future because they waste so little in the present. Their current dimness is a deposit into ages that have not arrived. A bright star spends its energy in a brilliant surge and disappears from the living population. A red dwarf saves its glow, releasing it with such restraint that the payoff is survival. In the far future, that faintness may be the main source of ordinary light. The infant quality of red dwarfs also matters for the search for life. Around some of these stars, planets may have existed for billions of years already. Some may have endured early turbulence, intense flaring, tidal stresses, and atmospheric loss. Others may have stabilized, keeping air and water in forms that remain uncertain to science. A long-lived star does not automatically create a habitable world. Time is necessary for life as known on Earth, but time alone is not enough. A planet must survive the star's youth, keep the ingredients for habitability, and avoid losing too much atmosphere or water. Red dwarfs offer duration, yet duration must be paired with protection. Since all red dwarfs are still early in their lives, the most important era for life around them may also lie ahead. The universe may not have reached the age when red dwarf planets become the dominant habitats, if they ever do. The planets detected around red dwarfs are not the final expression of those systems. They are snapshots from an opening age. Some may already be barren, some may be changing, some may hold conditions that future telescopes can test in the thin fingerprints of atmospheres. Yet the larger story remains incomplete, because the central stars themselves are nowhere near their endings. Red dwarfs are not remnants of a finished cosmic cycle. They are promises written slowly in hydrogen. Their most profound chapters belong to a universe that has not yet unfolded. In this way, red dwarfs change the scale of hope and uncertainty. They make the future of starlight less abrupt. They suggest that after the bright age fades, ordinary fusion may continue in countless small places, not as grand spectacle, but as persistence. The cosmos does not need to remain brilliant to remain active. It can glow faintly, locally, patiently. A red dwarf born in the early galaxy may still be burning when the sun is only a cooled remnant, and when many familiar stars have vanished from the living sky. To call such a star young is not poetic exaggeration. It is a statement about proportion. Its life is measured against a future so vast that the entire past of the universe becomes only the first breath. The red dwarf sits quietly in the dark, holding within its slow fusion the proof that cosmic time has barely begun to spend its longest light. At the lower edge of starlight, the boundary between a star and something almost a star becomes thin. A red dwarf may be small, but it is still a true star, held in balance by hydrogen fusion in its interior. Just below it, in mass and temperature, lies a stranger class of object, the brown dwarf. A brown dwarf forms in much the same dark nurseries where stars are born, gathering from collapsing gas and dust under gravity. It can be larger than the largest planets and can glow with leftover heat from its birth. Some can briefly fuse a heavier form of hydrogen, and the most massive can sustain limited reactions that make them seem star-like for a time, but they do not cross the lasting threshold that defines a main sequence star. They cannot keep ordinary hydrogen fusion going in a stable, long-lived way. This narrow divide makes the smallest red dwarfs especially important. They stand on the last step before failure, where a small change in mass decides whether an object becomes a lasting light or slowly cools into darkness. The distinction sounds simple, but it reaches into the deepest rules of stellar birth. A cloud fragment collapses because gravity pulls its material inward. As it shrinks, the center heats. If enough mass gathers, pressure and temperature become high enough for hydrogen nuclei to overcome their natural repulsion and fuse. The object then finds a steady balance. Gravity presses inward, fusion heats the gas, and outward pressure resists collapse. This balance can last for immense spans of time. If too little mass gathers, the center never becomes hot enough for sustained hydrogen fusion. The object may still be massive, hot, and luminous in its youth, but its light is temporary. It shines because it is cooling from formation, not because it has entered the slow economy of true stellar burning. Brown dwarfs are not failed because they are insignificant. They are failed only in one precise way: they never become stable hydrogen-burning stars. The smallest red dwarfs sit just above that threshold. They are only a little more massive than the heaviest brown dwarfs, yet that extra mass changes everything. More mass means stronger gravity. Stronger gravity means greater pressure and heat at the center. Once the core reaches the required conditions, hydrogen fusion can begin and continue. The star may be faint, cool, and barely above the limit of stardom, but it has crossed into a different future. It is no longer only cooling. It is making new energy from nuclear fusion. This gives it a life measured not in the fading warmth of birth, but in the slow use of hydrogen over time. A small red dwarf may look unimpressive beside the sun, yet beside a brown dwarf it has achieved something decisive. It has become a durable source of light. This threshold is not marked by a hard visible line in the sky. Nature does not label one object a star and the next a failed star with simple clarity. The transition depends on composition, age, internal structure, and mass. Objects near the boundary can be difficult to classify because young brown dwarfs can be warm and glowing, while the smallest red dwarfs are cool and dim. A young brown dwarf may resemble a tiny star for a while. An old red dwarf may appear modest and quiet. Astronomers must examine temperature, luminosity, motion, chemical signatures, and theoretical models to infer what lies inside. The question is why it shines, and whether its light is powered by sustained fusion or by the slow loss of stored heat. This makes the edge of stardom a place where appearance can mislead. A dim red point may be a star destined to burn for trillions of years, or an object that will fade without ever joining the main river of stellar life. The difference may be hidden in mass, in the deep center where the pressure either does or does not become enough. At this boundary, the universe shows how small changes can open radically different futures. A fraction more material can turn a cooling body into a star. A fraction less can leave it as a brown dwarf. Warm at first, then increasingly dark. Both may form from the same kinds of clouds and drift through the galaxy alone, with planets or disks, or orbiting other stars. Yet their destinies diverge. The red dwarf enters the long sequence of hydrogen burning. The brown dwarf slowly gives away the heat it gained while forming. It may remain detectable for a long time in infrared light, but it has no stable internal engine to renew that energy for trillions of years. The threshold is therefore not about size alone. It is about the ability to hold a nuclear fire in balance. These stars are often described as tiny, sometimes not much larger in radius than giant planets, because adding mass to dense low-mass objects does not always make them much wider. Their interiors are compressed, their surfaces cool, their light weak. Yet the smallest red dwarfs are not merely large planets. Planets can be complex, massive, stormy, magnetic, and hot from internal heat, but they do not sustain core hydrogen fusion. Brown dwarfs occupy the middle ground, more massive than planets but not fully stellar. Red dwarfs cross the line. They become part of the universe's population of long-lived suns, however faint. That crossing changes their relationship to time, to planets, and to the future darkness of the cosmos. A planet cools unless warmed by a star or by its own limited internal heat. A brown dwarf cools as well, though from a hotter and more massive beginning. A red dwarf can continue producing energy steadily for spans no planet or brown dwarf can match. It has joined the long-burning order of the universe. The smallest red dwarfs do not announce their success with brilliance. They may emit only a tiny fraction of the sun's light. Their habitable zones, if they have them, lie extremely close. Their planets may circle in tight orbits, pulled strongly by gravity and exposed to magnetic activity. Yet the star itself has crossed a cosmic test. It gathers enough mass to ignite ordinary hydrogen, and not merely for a brief stage. It becomes self-sustaining. Its faintness is the proof of how slowly it burns, not evidence that it barely exists. Being near the threshold may help extend its life. With so little luminosity, it spends fuel almost reluctantly. If its interior remains well mixed, it can keep delivering hydrogen into the region where fusion continues. The result is one of the longest stellar lifetimes possible. The universe's last true stars are likely to be descendants of this low-mass family, not because they are powerful, but because they are just powerful enough. The boundary with brown dwarfs also matters for the search for worlds. Around a red dwarf, planets can receive continuous warmth from fusion, though the closeness required introduces many hazards. Around a brown dwarf, a planet or moon may enjoy warmth only temporarily as the object cools. Its habitable zone, if one can be defined, would move inward over time as the brown dwarf fades. This makes lasting habitability far more difficult. A red dwarf's stable burning offers a steadier anchor. It may be dim and active, but it can maintain a relatively persistent output for extraordinary durations. That steadiness is what turns small stars into possible homes and brown dwarfs into more uncertain shelters. Both may hold strange environments, but only the red dwarf has the long nuclear patience that can keep a planetary system under a lasting low sun. The edge of stardom is therefore also an edge of possibility. It marks where cosmic bodies gain enough internal power to shape eras rather than moments. A brown dwarf may glow in youth, host companions, and drift through space like a shadowed lantern. But its light is a fading inheritance. A red dwarf, barely more massive, becomes a clock that can tick for trillions of years. This is why the smallest true stars carry such weight in the cosmic story. They show that the universe does not require grandeur to create endurance. It only requires the right conditions at the center, enough mass, enough pressure, enough heat, and a slow enough burn. Just above the threshold, a faint red object becomes one of the most durable forms of light that nature can make. Just below it, a similar object cools toward obscurity. Between them lies one of the quietest and most consequential borders in astronomy, where destiny depends on whether hydrogen can begin its long transformation into helium. The smallest red dwarf stands there like a narrow flame at the entrance to the stellar world, weak to the eye, immense to time, and proof that the difference between almost shining and shining for ages can be only a little more gravity in the dark. Around red dwarfs, the search for other worlds changes its scale. The star is small, dim, and cool, yet its surroundings may be crowded with planets. Modern surveys of exoplanets reveal that planets are not rare decorations around stars. They're common outcomes of star formation, built from disks of gas and dust that remain after a young star gathers most of its mass. Around red dwarfs, this fact becomes especially important because these stars themselves are so numerous. If the most common stars often carry planets, then the galaxy may contain vast numbers of worlds circling faint red suns. Many of those worlds may be rocky. Some may be similar in size to Earth. Some may orbit in places where temperatures allow liquid water under the right atmospheric conditions. This does not mean such worlds are living worlds, or even comfortable worlds. It means that the basic stage on which habitability might unfold may be far more common around red dwarfs than around stars like the Sun. A dim star therefore becomes a bright target for one of science's oldest questions, whether life is confined to one planet or scattered through the dark in many forms. The link between red dwarfs and planets grows from both abundance and detection. A planet passing in front of a star blocks a small fraction of the star's light. This is called a transit. Around a large, bright star, the shadow of a small rocky planet is tiny and difficult to measure. Around a red dwarf, the same planet covers a larger share of the star's face, so the dip in brightness is easier to find. Because the habitable zone around a red dwarf lies close to the star, planets in that region complete orbits quickly. They pass in front of the star more often, giving telescopes repeated chances to confirm their presence. This makes red dwarfs practical laboratories for exoplanet science. Their faintness, which hides them from ordinary sight, helps reveal the silhouettes of small worlds. In the lowered light of a small star, a rocky planet can leave a deeper mark. The result is a growing catalogue of systems that would once have been unknown compact families of planets, often packed close to their stars, orbiting in rhythms unlike the wide architecture of the solar system. These systems show that red dwarfs are not empty embers. They can be centers of complex planetary arrangements. Some hold multiple planets inside distances that would fit well within Mercury's orbit around the Sun. Others contain worlds larger than Earth but smaller than Neptune. a size range common in the galaxy yet absent from the solar system. Some planets are likely rocky, some may be wrapped in thick atmospheres, some may be water-rich, dry, volcanic, icy, or stripped bare. Distance alone cannot reveal the truth. A planet's mass, radius, density, orbit, star, atmosphere, and history all matter. Around a red dwarf, the possibilities multiply because the systems are compact and the stars endure. A planet that survives the hazards of youth may remain in a stable orbit for an immense time. The star offers duration, and duration gives planetary chemistry time to change, yet duration also gives danger time to work. The earlier stages of a red dwarf's life can be rough. Young red dwarfs may be more luminous at first than they later become, and many are magnetically active. Their planets form close to a star that may flare, emit strong ultraviolet and high-energy radiation, and change its brightness in ways that challenge atmospheres. A world that sits today in the habitable zone may have spent its youth under much harsher conditions. It may have lost water before the star settled. It may have developed a thick blanket of greenhouse gases, or it may have had its atmosphere thinned by radiation and charged particles. Habitability around red dwarfs is therefore not a simple matter of where a planet orbits now. It is also a question of what happened long before the present moment. A planet's current position may look promising, while its past may have already decided its fate. This is one reason the red dwarf search remains both hopeful and cautious. Their numbers are enormous, but every planet carries a history that cannot be read from distance alone. Still, the promise is difficult to ignore. A galaxy rich in red dwarfs is a galaxy rich in potential planetary real estate. Even if only a small fraction of these stars host worlds with stable atmospheres and surface water, the total number could be large. The search for life does not require every red dwarf planet to be friendly. It only requires some of them to be possible. The odds become powerful when multiplied by the population of stars. Red dwarfs may host many planets in or near temperate regions, and because they live so long, some of those planets may have more time than Earth has had. On Earth, life appears to require stable liquid water, chemistry able to store and copy information, and energy sources that keep reactions moving. Red dwarf planets could, in principle, offer these ingredients, but arranged in unfamiliar ways. Their skies would be darker, their stars would loom larger if the planets orbit close enough. Their days might be locked to their years, their weather, oceans, and magnetic environments might follow rules shaped by proximity rather than distance. Such worlds are not second Earths waiting quietly under red light. They are their own category of possible habitat. The question is not whether they match Earth perfectly, but whether they can maintain the conditions life needs for long enough. One of the most important future tools in this search is the study of atmospheres. When a planet transits a red dwarf, a little starlight can pass through the planet's atmosphere, if one exists, before reaching a telescope. Different gases absorb different wavelengths of light. In principle, this allows astronomers to look for signs of water vapor, carbon dioxide, methane, oxygen, or other chemicals that reveal something about the planet's air. These measurements are difficult, especially for small rocky planets, but red dwarfs make them more achievable because the planets are relatively large compared with their stars. A thin atmospheric signal can stand out more clearly than it would around a larger star. This is why nearby red dwarf systems become prime targets. They are not chosen because they are guaranteed to be habitable. They are chosen because they are among the few places where the question can be tested. A dim star becomes useful precisely because its small size lets a planet speak more loudly through the light it blocks and filters. Yet the interpretation of such signals will be delicate. A planet might show gases produced by geology rather than life. Oxygen can arise in some scenarios without biology. Methane can come from non-living chemistry. Water vapor may indicate an atmosphere, but not necessarily a stable ocean. Around red dwarfs, stellar activity can alter atmospheric chemistry, creating or destroying molecules in ways that complicate the search. A flare can change the radiation environment. A weak or lost atmosphere can leave only surface minerals to interact with light. A thick haze can hide deeper layers. The search for life around red dwarfs will therefore move slowly from detection to atmosphere, from atmosphere to climate, from climate to cautious biological possibility. The stars may be abundant, but certainty will remain rare. The aim is not to force life into the data, but to learn which worlds have truly remained open to it. The worlds around dim suns expand the geography of hope without removing the difficulty. They may include dry rocks baked by early radiation, ocean planets wrapped in steam, tidally locked worlds with one bright hemisphere and one frozen night, moons warmed by tides, and dense rocky planets holding atmospheres under red skies. Some may be sterile from the beginning, some may pass through brief habitable windows, some may endure. The sheer number of red dwarfs means that the universe may have run this experiment countless times, with different starting materials, different histories, and different outcomes. In that multiplication lies the mystery. Red dwarfs are not merely long-lived stars waiting at the edge of visibility. They are possible centers of planetary stories, each one turning quietly through the dark, each one carrying evidence that telescopes are only beginning to read. Around them, the search for life becomes less like the hunt for another solar system and more like the study of a vast hidden population. These dim suns may host worlds unlike Earth in nearly every outward way, yet some may still keep warmth, air, water, and time. In the weak red light of the galaxy's smallest stars, the question of life does not shrink, it spreads. Around a red dwarf, warmth gathers close to the source. The star is cool and faint, so a planet that hopes to keep liquid water on its surface cannot drift at Earth's distance and expect familiar sunlight. It must move inward, often to an orbit far tighter than Mercury's path around the Sun. There, the dim star may provide enough energy for seas, clouds, rain, and chemistry, but the same closeness changes almost everything about the planet's life. The habitable zone, the region where surface water could remain liquid under the right atmospheric pressure, becomes narrow and intimate. It sits near the star, where gravity is stronger, orbital periods are shorter, and the planet's environment is shaped by forces that Earth avoids by living farther from a brighter sun. This is the central tension of red dwarf worlds. The star lasts for astonishing spans of time, but its temperate region lies so close that habitability comes wrapped in risk. Hope tightens into danger, not because liquid water is impossible, but because keeping it becomes more complicated than a circle around a gentle light. The first major consequence is tidal locking. Gravity does not merely pull a planet along its orbit, it also raises tides, stretching the planet slightly toward the star. Over time, this tug can slow the planet's rotation until one hemisphere always faces the star, while the opposite hemisphere remains turned towards space. The Moon is tidally locked to Earth, showing the same face as it orbits. A close planet around a red dwarf can enter a similar state with its star. If that happens, the planet no longer has a normal day and night cycle across its whole surface. One side receives continuous starlight, the other lies in permanent darkness. Between them is a border region where the star may hang low near the horizon in an endless twilight. Such a world sounds hostile at first, divided between heat and cold, but the reality depends on air, water, clouds, And circulation. A planet without a thick atmosphere might become extreme, with the day side baking and the night side freezing. A planet with enough atmosphere might move heat from the illuminated hemisphere into darkness through winds. A world with deep oceans might transfer energy through currents, softening the divide. The locked state is not automatically fatal, but it forces climate into unfamiliar shapes. Instead of seasons driven mainly by tilt and orbit, the main pattern may be a permanent star-facing weather engine, with clouds forming near the substellar point, the place where the star stands overhead, and winds carrying warmth outward. Thick reflective clouds on the day side could help protect a planet from overheating, while atmospheric circulation might keep the night side from freezing. Yet models are not guarantees. They depend on surface pressure, ocean depth, rotation rate, atmospheric chemistry, and water loss around red dwarfs. The question is rarely whether one factor allows life. It is whether many factors align for long enough. The close orbit also exposes a planet to stronger tides inside its body. Just as the star can slow rotation, it can flex the planet's interior. This flexing turns orbital energy into heat, a process called tidal heating. In moderation, internal heat can keep geology active. It can drive volcanoes, recycle gases, and help maintain a carbon cycle that stabilizes climate over long periods. In excess, it can become destructive. Too much tidal heating could produce widespread volcanism or help turn a world into something closer to an overheated volcanic planet than a stable ocean-bearing one. The outcome depends on the planet's orbit. If the orbit is nearly circular, tidal heating may be limited. If the orbit remains stretched by interactions with other planets, the constant squeezing can persist. In compact red dwarf systems, neighboring planets may tug on one another, maintaining slight eccentricities or departures from circular paths. A small difference in orbit can mean a large difference in internal heat. A planet cannot be understood alone. Its habitability may depend on the gravitational rhythm of its neighbors. The narrow habitable zone also changes the planet's relationship with radiation. At close range, the planet receives starlight from a star that may be dim overall but active in bursts. Even during quiet periods, the spectrum of a red dwarf differs from that of the Sun. More of its energy arrives as red and infrared light. While the amount of visible light is lower, photosynthesis, if it developed, might adapt to different wavelengths, light levels, and rhythms of stellar activity. For climate, infrared light interacts strongly with atmospheric gases and clouds, affecting how heat is absorbed and redistributed. The star's color is therefore not merely scenery. It enters the physics of the planet's air and water. In the close habitable zone, even a modest change in stellar output can matter. If the star brightens or dims, the planet has less orbital distance as a buffer. A shift in incoming energy may push a marginal world toward ice or toward runaway heating. The inner edge of the zone is especially dangerous to too close, and water vapor rises into the upper atmosphere, where radiation can split it apart. Hydrogen, being light, can escape into space. Over time, a planet can lose its water. This process may have been especially severe during the early lives of red dwarfs, when many were brighter relative to their later stable state. A planet now sitting in a temperate orbit may have spent its youth receiving too much energy, with oceans turning to vapor and escaping before the star settled. The present habitable zone can therefore be misleading. It marks where conditions might work now, but it does not restore what was lost in the past. A dry world can sit in the right orbit and remain dry forever, unless water arrives later or survives in hidden reservoirs. The outer edge has its own problem. Too far from the red dwarf, a planet may freeze unless greenhouse gases trap enough heat. Carbon dioxide can help warm a world, but too much changes atmospheric pressure, chemistry, and surface conditions. A planet near the outer edge might become a snowball, its oceans sealed beneath ice, perhaps still active below, but cut off from the kind of surface environment most familiar from Earth. The habitable zone is not a promise of comfort. It is a region of possibility, bounded by climate feedbacks and shaped by planetary history. For red dwarfs, that region can be close enough that the boundaries are sharpened by tidal locking, flares, and atmospheric escape. The term habitable zone can sound broad and inviting, but around a small star it becomes more like a thin corridor through competing hazards. Yet narrow does not mean empty. The closeness that creates danger also helps astronomers find these planets. Their short orbits produce frequent transits. Their gravitational pull on the star can create measurable wobbles. Their atmospheres, if present, may be studied more easily because the star is small. The same compactness that may threaten air and water also brings these worlds within reach of measurement. Science can begin to separate worlds that merely occupy promising orbits from worlds that actually keep atmospheres. The first step is location. The deeper step is survival. A planet must not simply reside in the habitable zone. It must have passed through formation, early radiation, tidal evolution, impacts, volcanic change, and atmospheric chemistry without losing the conditions that matter most. This is why red dwarf planets sit at the edge of modern uncertainty. They are among the most numerous candidates for life, yet their environments may be unlike anything directly known. A tidally locked ocean planet might keep a ring of habitable climate between a bright cloudy hemisphere and a frozen night. A dense atmosphere might turn permanent day and night into a global circulation system rather than a fatal divide. A dry planet with a thin atmosphere might fail quickly. A world with too much internal heat might lose stability from below. Every possible refuge has a condition attached. Every hazard has an exception. The narrow habitable zone is therefore not a simple verdict, but a testing ground. Red dwarfs ask whether life needs an Earth-like arrangement, or whether it can persist under stranger skies, closer to a smaller sun, with one face held in light and one in darkness. They ask whether oceans can move enough heat, whether atmospheres can survive storms, whether geology can remain active without becoming violent, and whether chemistry can find stability in a world locked to a star that will outlive nearly all others. The answer remains unknown. Around red dwarfs, habitability is not spread across wide, comfortable distances. It is compressed near the star, where gravity, light, heat, and time crowd together. The prize is immense duration. The cost is exposure. In that close red twilight, the possibility of living worlds does not vanish. It becomes more delicate, more conditional, and more revealing than any simple copy of Earth. A red dwarf can appear peaceful from far away, a faint point of cool light that seems almost too quiet to threaten anything. But the surface of many red dwarfs tells a less gentle story. These stars can be magnetically restless, marked by dark star spots, sudden flares, and bursts of radiation that reshape the environments of nearby planets. A star spot is a cooler region on the stellar surface, created where strong magnetic fields disturb the movement of hot gas. On the Sun, sunspots come and go as part of a cycle, while Earth remains protected by distance, atmosphere, and magnetic shielding. Around a red dwarf, the situation can be far more severe because the planets of interest orbit close. A spot that would be only one feature on a distant sun-like star can matter more when the entire habitable zone lies near the source. The star is dim, but its activity can be intense. A planet may receive steady warmth for ages, then endure changes that test the survival of its atmosphere, oceans, and chemistry. This is why a refuge around a red dwarf can become unstable. Star spots can cover large portions of an active red dwarf's surface. Because these stars are cool to begin with, darker regions can reduce the total light reaching a planet. If the spot coverage changes, the planet's climate may feel the difference. A world near the outer edge of the habitable zone could be pushed toward deeper freezing during prolonged dim periods. Ice can reflect incoming light, which may strengthen cooling once it begins. On another world, thick greenhouse gases or ocean circulation might buffer the change. Clouds, atmospheric pressure, and heat storage can turn a sharp stellar variation into a softer climatic response. But the challenge remains. Around red dwarfs, the habitable zone is close and often narrow, so shifts in stellar brightness can be consequential. A planet may depend on a careful balance, and star spots can move that balance back and forth across thresholds that matter for water. The star's surface becomes part of the planet's climate system, not merely a light in the sky. Flares add a more sudden hazard. A flare is a rapid release of magnetic energy from the stellar atmosphere. In minutes, a red dwarf can brighten strongly at high energy wavelengths, sending ultraviolet radiation, X-rays, and charged particles into space. Some flares may be modest. Others can be powerful enough to change the upper atmosphere of a close planet. The visible brightening may fade quickly, but the consequences can last longer. High-energy radiation can break apart molecules, drive chemical reactions, heat the upper atmosphere, and help lighter gases escape. Charged particles can interact with magnetic fields or, if a planet lacks strong protection, reach deeper into the atmosphere. Over long spans, repeated flares may erode air, strip away protective layers, and alter the chemistry needed for stable surface conditions. A single flare may not decide a world's fate. A long history of flaring can. This creates a difficult contradiction. A planet must orbit close enough to avoid freezing, but that closeness places it near the star's magnetic weather. The same location that allows liquid water can also expose the atmosphere to erosion. If a planet has a strong magnetic field, it may deflect some charged particles, though magnetic shielding is not a perfect wall. If it has a dense atmosphere, the outer layers may absorb harmful radiation before it reaches the surface. If it has oceans, water can provide additional protection for life below the surface. But all of these protections depend on history. A magnetic field may weaken as a planet cools. An atmosphere may already have been lost during the star's early active phase. Water may have escaped after being split by radiation. The planet seen today may carry invisible scars from events billions of years old. Around red dwarfs, habitability is therefore not a static location. It is a record of survival through magnetic time. The chemistry of an atmosphere can be transformed by this activity. Ultraviolet light is important for many reactions. Too little can slow some forms of prebiotic chemistry, the chemistry that may help simple molecules become more complex before life begins. Too much can destroy fragile molecules or remove gases that protect the surface. Flares may briefly supply energy that drives useful reactions, while also threatening any atmosphere that has already formed. This makes red dwarf planets chemically ambiguous. Stellar activity can create gases that might be mistaken for biological signs. It can also erase gases that life would otherwise produce. Oxygen, for example, is not always a simple signal of living processes. If water vapor is split high in an atmosphere and hydrogen escapes, oxygen can remain behind under some conditions. Methane can be destroyed quickly in active radiation environments. A telescope reading such a planet's air must separate biology, geology, and stellar chemistry. The star does not merely illuminate the atmosphere, it participates in making it. The problem grows more complex because red dwarfs are not all alike. Some are relatively quiet, especially as they age. Others remain turbulent, producing frequent flares and showing large magnetic regions. Mass, rotation, age, and internal structure all influence activity. A rapidly rotating young red dwarf may be much more violent than an older, slower one. Yet even older red dwarfs can remain magnetically active longer than many larger stars. The history of a planet's star becomes as important as its present brightness. A calm red dwarf today may have been harsh when its planets were young. A system that now looks inviting may have passed through an early era of atmospheric loss. Conversely, a planet with a deep initial ocean, strong gravity, or a replenished atmosphere might endure conditions that would ruin a smaller or drier world. The question is not whether red dwarfs are safe or unsafe as a class. They're too varied for a single answer. The question is, which combinations of star and planet create a long-lived shelter instead of a slowly stripped stone? Stellar activity also complicates the search for planets themselves. When a planet transits, it causes a dip in starlight, but spots also change the star's brightness, and flares can produce sudden increases. These signals can blur estimates of a planet's size, orbit, and atmosphere. The small size of red dwarfs makes rocky planets easier to detect, but their active surfaces can hide a planet's true nature behind magnetic noise. Patterns must be separated from disturbances, and the planet's shadow must be distinguished from the star's restless face. For life, surface conditions may depend on where protection remains possible. A tidally locked world with a dense atmosphere might move heat well enough to avoid frozen darkness, while its atmosphere absorbs much of the star's high-energy radiation. Life, if present, might survive underwater, underground, beneath ice, or in regions where atmosphere and surface provide shielding. The day side might face radiation stress, while the night side might be cold but protected from direct flare light. Twilight regions could offer moderated temperatures. These possibilities do not prove life can thrive there. They show that the boundary between habitable and uninhabitable may be more subtle than a simple exposed surface. Red dwarf planets are not easy homes, but they widen the imagination of where protection and energy might overlap. A red dwarf's instability also has a far future dimension. The youngest ages may be the most hazardous, but once a suitable planet survives, the star's long lifetime becomes an immense advantage. A world that keeps its air and water beyond the early violent phase may have vast stretches of relative stability ahead. Flares may continue, but perhaps at moderate levels. Star spots may dim the light, but climate systems may buffer them. Chemistry may adapt to the star's spectrum. In that case, the very star that once threatened habitability could become a lasting source of warmth, offering not a perfect Earth-like environment, but a durable one. The path is narrow, and perhaps many planets fail along it. Yet the number of red dwarfs is so large that even a narrow path may be travelled somewhere. The fragile atmospheres of these worlds are therefore central to the mystery. They are the thin boundary between a planet and space, between radiation and surface, between water held close and water lost forever. Around a red dwarf, an atmosphere must survive dim seasons of spotted light, sudden storms of flare energy, early brightness, tidal locking, chemistry, escape, and time. A bare rock in the right orbit is only a memory of possibility. A planet with a stable atmosphere is still in the story. Red dwarfs offer the universe's longest-lasting hearths, but they do not offer them gently. Their small flames are magnetic, changeable, and sometimes severe. In their glow, hope is not erased, it is tested, again and again, by the restless surface of a star that may outlive nearly everything else. Life under a red sun would not begin as a familiar Earth with a different color of sky. It would begin as a negotiation between protection and energy, between a star that gives little steady light and a star that may sometimes release too much. The worlds most often imagined around red dwarfs are close worlds, perhaps locked with one face in constant day and one face in constant night. Such places seem divided by extremes, but planets are not only surfaces under light. They are moving systems of air, water, rock, ice, and chemistry. If life has any chance under a red dwarf, that chance may come from the ways these systems soften the star's harshest conditions. An ocean can store heat and move it across a globe. An atmosphere can carry warmth into darkness and shield a surface from radiation. Ice can preserve hidden seas. Rock can release gases and recycle carbon through long geological cycles. A red dwarf planet does not need to be a mirror of Earth to be interesting. It needs a stable path through its own dangers. The first possible shelter is the atmosphere. Without air, a close rocky world becomes exposed to space, losing heat quickly on the night side and absorbing radiation directly on the day side. With enough air, the situation changes. Winds can rise from the heated hemisphere, move toward the colder side, descend, and return, creating a circulation pattern unlike Earth's but still capable of redistribution. A dense atmosphere could prevent the dark hemisphere from becoming a permanent trap of frozen gases. It could spread warmth into twilight regions and perhaps across the entire planet. The composition matters. Carbon dioxide traps heat. Water vapor participates in clouds and warming. Nitrogen can add pressure and help move heat, even if it is not a strong greenhouse gas itself. Too little atmosphere leaves the surface fragile. Too much may crush the climate into a heavy greenhouse state. Between those extremes lies a range where air becomes not merely a blanket, but a bridge between day and night. Oceans may be the second great stabilizer. Water absorbs heat slowly and releases it slowly, creating a kind of planetary memory. On a tidally locked world, a deep ocean could carry warmth away from the star-facing side through currents and return colder water from the night side. This movement might prevent the day side from overheating and the night side from freezing completely. Sea ice could form in darkness, while open water remains beneath or closer to the light. A planet with a global ocean might develop weather dominated by the permanent star overhead, with clouds near the brightest point and currents flowing through a climate that never experiences a normal sunrise or sunset. If life begins there, it may not care about the absence of an Earth-like day. Microbes in oceans, vents, sediments, or under ice could live by chemical gradients, minerals, and dissolved gases as much as by sunlight. Around a red dwarf, water is not only a surface feature, it may be the planet's main defense against extremes. Moons and large rocky planets widen the possibilities. A moon orbiting a giant planet in the temperate zone of a red dwarf could receive energy from the star and also from tidal forces created by its parent planet. Such tidal heating might help maintain subsurface oceans, as similar processes are considered important for icy moons in the solar system. Too much heating would be damaging, but moderate heating could keep water liquid below ice, power chemical reactions at the seafloor, and create habitats shielded from flares. Large rocky planets, sometimes called super-Earths, may hold advantages if their gravity helps them retain atmospheres against escape. Greater mass can help hold air, though it may also create thick atmospheres and high pressures that differ greatly from Earth. A massive rocky world around a red dwarf could be stable, volatile rich, and geologically active for a long time, or it could become an oppressive greenhouse world. Habitability is not a single ingredient. It is a balance among many. Light under a red dwarf would also reshape biology, if biology exists there. These stars emit much of their energy in red and infrared wavelengths. On Earth, plants use visible light in ways shaped by the sun's spectrum and by the chemistry life happened to inherit. On a red dwarf planet, photosynthesis might use different pigments, different light harvesting strategies, or might be limited by lower visible light levels. Some organisms could depend more heavily on infrared light, though the details remain uncertain. In oceans, red and infrared light are absorbed differently from shorter wavelengths, so aquatic photosynthesis could follow unfamiliar rules. Life might gather in shallow water beneath protective films, inside rocks, or under translucent ice. The surface could be only one habitat among many, and perhaps not the most reliable. A planet's interior may matter as much as its sky. Geological activity helps regulate climate on Earth by cycling carbon between air, ocean, rock, and mantle over long timescales. Around a red dwarf, such regulation could be crucial. If volcanic gases replenish an atmosphere eroded by stellar activity, a planet may recover from losses that would otherwise be fatal. Yet geological activity depends on size, composition, water, internal heat, and perhaps tides. A small planet may cool too quickly. A tidally stressed planet may overheat. A larger world may keep internal heat longer. Life, if it arises, might depend on the hidden rhythm of stone as much as the visible light of the star. The most protected habitats may be beneath surfaces. On Earth, life exists deep underground, in ocean sediments, inside rock, around hydrothermal vents, and in places where sunlight is absent. This widens the meaning of habitability around red dwarfs. A planet battered by flares might still host life below water, beneath ice, or underground, where radiation is reduced and temperatures change slowly. A moon with a buried ocean could remain biologically interesting, even if its surface is frozen and dark. In such environments, energy may come from chemical reactions between water and rock, from volcanic heat, or from tidal flexing rather than direct starlight. These possibilities do not make life likely by themselves, but they prevent the surface from being the only judge. A red dwarf may be harsh above, while hidden niches below remain calm enough for chemistry to persist. The challenge is that life also needs beginnings. Protected environments may preserve life once it exists, but the origin of life may require cycles of wetting and drying, ultraviolet energy, mineral surfaces, or other conditions that are still debated. Red dwarfs complicate this question. Their light may provide less of some useful ultraviolet radiation, while their flares may provide too much in sudden bursts. A tidally locked planet may have stable regions but fewer familiar cycles. Oceans may protect molecules but also dilute them. The origin of life under a red sun could follow Earth-like pathways in modified form, or it could require settings that Earth science has not yet fully imagined. This uncertainty is not a weakness of the question. It is the reason red dwarf worlds remain scientifically alive. They force the search for life to separate what is essential from what is merely familiar. If life does endure under a red sun, its world may be calm in ways that seem strange. The star would not race through its life. Once the early violent era passes, a moderate red dwarf could give a planet enormous time. Evolution, if it begins, could unfold beneath a sky ruled by a small steady sun, with weather patterns anchored to permanent light and darkness. A biosphere might remain microbial for billions of years. It might never produce complex organisms, or, under rare, favourable conditions, it might become diverse in forms shaped by dim red light, strong tides, and long stability. The point is not that red dwarfs guarantee life. They do not. The point is that their planets may explore a wider climate and biological space than Earth alone can define. Life under a red sun is therefore a question of endurance. It asks whether atmospheres can hold, whether oceans can move heat, whether geology can renew air, whether chemistry can begin, and whether living systems can shelter through flares and time. Some planets will be stripped and silent. Some will be locked in ice or steam. Some may hide water below dark crusts. A few may keep the delicate combination of protection, energy, and stability that turns a planet from a body in space into a living environment. Around red dwarfs, the possibilities are neither easy nor empty. They are conditional, numerous, and strange. In the red light of the galaxy's stars, life may not resemble the open blue brightness of Earth. It may be buried, twilight-bound, oceanic, microbial, patient, and ancient. It may survive not by escaping the star's difficulties, but by finding the narrow places where those difficulties become survivable. The future of humanity, if it reaches far enough, is not bounded by the present warmth of the sun. Earth feels permanent because human history is short, because mountains and oceans outlast generations, and because the sun rises with such steady familiarity that its change is almost invisible. But the sun is a star, and stars evolve. Its brightness slowly increases as its core changes, and long before it reaches the dramatic red giant stage. Earth's surface may become too warm for complex life as it is known today. Oceans may begin to change, weathering, carbon dioxide, clouds, and the balance of heat may shift beyond the range that has allowed the biosphere to remain stable for so long. The end of Earth's habitability is not the same as the end of humanity if intelligence survives, adapts, and learns to move beyond its first world. But it does mean that the human future cannot remain tied forever to one planet under one yellow star. Eventually, survival becomes an astronomical question. In that question, red dwarfs appear not as dramatic destinations, but as the most abundant long-term shelters the galaxy offers. Their importance begins with their numbers. A civilization looking outward across the Milky Way would find that small red stars are everywhere. They lie in the local neighborhood, in older populations, in quiet corners of the galaxy, and in systems too faint to have entered ancient human sky maps. Their faintness makes them difficult landmarks, but their abundance makes them unavoidable. For a species that must eventually leave its original star, the galaxy is not mainly a field of sun-like replacements. It is a field of red dwarfs, each with its own history, activity, planets, and hazards. Some would be useless as homes. Some would be too active, barren, dry, unstable, or poor in accessible resources. Others may hold planets, moons, asteroids, ice, metals, and stable orbits. The search for refuge would not be a search for perfection. It would be a search for workable systems, places where energy, materials, and time overlap. Red dwarfs offer time in extraordinary abundance. A civilization that settles near a suitable red dwarf would not gain a bright sky or an easy Earth. It would gain duration. The star could shine through spans far longer than the remaining life of the sun. Around it, habitats might be built on planets, in orbit, inside hollowed asteroids, or within artificial structures that collect the star's weak light with patience rather than force. The star's low output would require economy. Its habitable zone would be close and possibly dangerous. Its flares, if active, would need shielding. But a civilization able to travel between stars would likely already understand how to build protection against radiation, regulate climate inside constructed environments, recycle water, and use energy carefully. For such a civilization, a red dwarf might not need to provide an Earth-like surface. It might only need to provide a stable gravitational center, long-lasting energy, and a planetary system rich enough to support construction and renewal. This changes the meaning of habitability. In early biology, a habitable world must protect chemistry without technology. It must supply air, water, energy, and stability naturally. For a technological civilization, habitability can be partly engineered. A bare rock may become useful if it has metals, volatiles, and orbit. A frozen moon may become a reservoir. A tidally locked planet may be difficult on the surface, but its shadowed regions, subsurface layers, or orbital neighborhood may still be valuable. The red dwarf itself becomes a power source to be managed. Its light is dim, but a collector spread across a wide area can gather it. Its heat is modest, but steady. Its lifetime is the true resource. Where the sun offers a generous present and a limited future, a red dwarf offers a sparse present and an immense future. The bargain is difficult, but not meaningless. A far future civilization may choose patience over brightness, because patience is what remains. The path to such a future is not simple. Distances between stars are enormous, and moving living beings, machines, or self-replicating systems across interstellar space requires energy and timescales far beyond present human activity. Red dwarfs are common, but common does not mean close enough to reach easily, and reaching one does not mean finding a ready home. A system may lack planets. Its planets may have lost atmospheres. Its young history may have sterilized surfaces. It may flare in ways that complicate settlement. Even a calm red dwarf system would require adaptation to low light, tight orbits, and unfamiliar resources. The idea of red dwarfs as humanity's last homes is therefore speculative, but it is grounded in a simple fact of stellar evolution. When brighter stars age and disappear from the main sequence, red dwarfs remain. Any civilization seeking long continuity must reckon with the stars that last longest. The timescales involved make ordinary historical planning seem almost weightless. Human civilization is only thousands of years old. Agriculture, cities, writing, industry, and spaceflight occupy a brief interval compared with the age of Earth. The future habitability of Earth may still extend for hundreds of millions of years, perhaps longer in some forms, but the Sun's long-term evolution places an ultimate boundary on the planet's surface comfort. Red dwarfs extend the horizon from millions and billions into trillions of years. They invite a form of thinking in which survival is no longer about a single migration, a single colony, or a single planet. It becomes a chain of continuity through changing cosmic conditions. A civilization might move from young bright stars to older dim ones, from planetary surfaces to constructed habitats, from local resources to carefully managed energy economies. Around red dwarfs, civilization would have to become quiet in the same way the star is quiet, efficient, shielded, patient, and adapted to faint abundance. There is a strange symmetry in this possibility. Life on Earth begins under a star bright enough to support open oceans, weather, photosynthesis, and complex ecosystems. If humanity ever reaches the far future, it may survive under stars that human eyes could never see from Earth without instruments. The first home is a blue world under a yellow sun. The last homes, if any exist, may be sealed habitats or adapted worlds under dim red light. this story would move from brightness to endurance, from a generous natural cradle to carefully maintained shelters in the long dark. This is not despair, it is a widening of scale. The universe does not promise permanent comfort, but it offers long-lived structures. Red dwarfs are among those structures, and their quietness may become valuable when the brighter phases of cosmic history have passed. Yet even this vision remains bounded. Red dwarfs do not last forever. Their fuel is finite. Their planets can be altered by time. Galaxies themselves evolve. Close stellar encounters, orbital changes, and the long decline of star formation shape the future environment. The red dwarf is not eternal salvation. It is a reprieve of extraordinary length. That distinction matters. Speculation remains honest only when it keeps the ending in sight. Red dwarfs may provide the longest ordinary stellar futures, but not an escape from change itself. For humanity, the meaning of red dwarfs may therefore be less about certainty than perspective. They show that the future is not only a countdown to the sun's transformation, it is also a landscape of alternatives, harsh and distant but real in principle. They make the galaxy look less like a scattering of bright suns and more like a reservoir of faint endurance. Around them, life may arise naturally, struggle, fail, or persist. Around them, intelligence may one day seek shelter, whether human or not. A red dwarf system with the right conditions could become a haven, a workshop, a library, or a quiet harbour in deep time. It would not resemble Earth at noon. It might be darker, colder, more enclosed, and more dependent on careful design. But it could offer what every long future requires time to continue. The idea remains speculative, yet it rests on the known patience of small stars. The sun gives Earth its beginning, but it does not own every possible ending. Beyond it, the galaxy is filled with dim stars that wait through ages, holding their fuel, warming their close worlds, and carrying ordinary light into eras where most stars like the sun are gone. If humanity survives long enough to leave its cradle, it may find that the best future is not around the brightest star, but around one of the faintest. In the long migration of cosmic time, the red dwarf becomes not a last hope in the language of panic, but a last hearth in the language of endurance, small, guarded, difficult, and still shining when the universe has grown quiet. The last living stars do not end with thunder. A red dwarf spends its life so slowly that its ending belongs to an age no telescope can observe. Beyond the present history of galaxies, planets, and every star now visible to ordinary sight, in the current universe, red dwarfs remain in their steady hydrogen-burning phase, still mixing fuel through their interiors, still turning the simplest atoms into helium with restrained patience. Their final evolution is therefore not a record written in the sky, but a prediction drawn from the physics of pressure, temperature, fusion, and time. Larger stars reveal their endings all around the cosmos. They swell, shed layers, collapse, explode, or leave glowing remnants. Red dwarfs offer no completed examples. Their future must be followed in models that extend far beyond the age of the universe. Yet the broad story is clear enough to be haunting. These small stars do not have the mass to die as supernovae. They do not build heavy elements in a sequence of violent furnaces. They do not tear themselves open in a bright final act. They fade by using what they have almost completely, and their faintness becomes the reason they are among the last ordinary stars still alive. Through most of its life, a red dwarf remains on the main sequence, the long stable period when hydrogen fusion supplies its light. Inside the smallest red dwarfs, convection keeps the star stirred, bringing hydrogen inward and carrying helium outward. This mixing prevents the core from aging in isolation. A star like the Sun gradually builds a helium-rich center, while much of its hydrogen remains outside the region where fusion is most efficient. A fully convective red dwarf can draw on a larger share of its total fuel. This gives it an astonishing future, but not an endless one. Every fusion reaction changes the star. Hydrogen becomes helium. The balance of particles shifts. The star slowly grows more helium-rich, and its internal structure responds. Over trillions of years, the reservoir declines. The red dwarf does not suddenly run out of fuel like a lamp going dark. It changes by degrees as the chemistry of its whole body moves toward a new state. In that remote era, some red dwarfs are expected to grow hotter at the surface as they age. This seems counterintuitive, because stars are often imagined as cooling when they approach death. But red dwarf evolution is not the same as the path followed by the Sun. Since the star uses its fuel so completely and remains compact, its outer layers may become hotter and bluer while its luminosity changes. The predicted result is sometimes called a blue dwarf, not because such objects have been seen, but because the old red dwarf may shift toward higher surface temperatures before it fully exhausts its hydrogen. No blue dwarf exists in the observable universe today, because the universe is too young for even the oldest red dwarfs to have reached it. This possible blue dwarf stage is not a return to youthful power. It is the late adjustment of a star that has spent nearly all its usable hydrogen. Its light may become less red, but it remains a low-mass object approaching the end of fusion. The change shows that the final life of a red dwarf is not simply a slow dimming from beginning to end. For any planets or habitats still nearby, this would alter the flow of energy after ages of relative stability. A world that once sat comfortably in the red dwarf's habitable zone might receive changing radiation and heat. The habitable region itself could move. Oceans, atmospheres, and climates, if any remain, would face an old star no longer behaving exactly as it did through its long youth. Even the most patient shelter changes eventually. When fusion can no longer continue, the red dwarf's stellar life comes to an end. It does not have enough mass to ignite the later stages that larger stars may enter. It cannot fuse helium into heavier elements in a sustained way. The internal furnace quiets. What remains is a dense stellar remnant, a white dwarf, likely composed largely of helium for the lowest mass red dwarfs. A white dwarf is not a star in the main sequence sense, because it no longer produces energy through steady fusion. It shines because it is hot from compression and from the energy left inside it. Gravity squeezes it strongly, but it is held up by a quantum pressure that arises when matter is packed into an extremely dense state. A red dwarf can spend trillions of years releasing energy from hydrogen fusion, then leave behind an object roughly planetary in size, but with a mass that may still be a significant fraction of a star. The white dwarf's matter is not like ordinary rock or gas. It is compressed into a state where the familiar spaces inside atoms are largely overcome. This remnant may glow white, blue-white, or another pale color depending on its temperature. But its glow is no longer renewed in the old way. It has become a cooling body. Time, which once worked in partnership with fusion, now works only as loss. The white dwarf radiates heat into space. Slowly, incredibly slowly, it cools. In the present universe, many white dwarfs exist, but none has cooled all the way to the final dark state, because there has not been enough time. The next stage is the black dwarf, a cold remnant that has lost nearly all visible warmth. Like the blue dwarf, the black dwarf is expected by theory but not observed. The universe is too young for any white dwarf to have cooled completely into that final condition. The name sounds dramatic, but the process is quiet. A black dwarf is not a black hole. It is not a collapse into a bottomless gravity well. It is a cooled white dwarf, a stellar remnant that no longer shines meaningfully. It would drift through space as a dark, dense object, carrying the memory of a star that once fused hydrogen for a span beyond current imagination. Its darkness would not be sudden. It would arrive through cooling so gradual that the difference between 1 trillion-year interval and the next would be almost invisible. The final fading of red dwarfs therefore extends the stellar age of the universe, then helps populate the later cosmos with remnants. The last ordinary stars may be red dwarfs, but the last objects are not stars in the familiar sense. They are white dwarfs, black dwarfs, neutron stars, black holes, cold planets, and other remains moving through a universe where new star formation has dwindled. Red dwarfs matter because they delay that darkness. They carry fusion into the far future, long after brighter stars have completed their lives. But when their hydrogen is finally spent, they join the general movement from light to residue. Their endurance changes the timing of the universe's twilight, not the fact that twilight comes. This is the calm severity of stellar evolution. Even the most frugal flame spends fuel. For any life or intelligence that depends on red dwarfs, their final stages would mark the end of the longest natural refuge. A civilization that has moved from short-lived stars to long-lived ones might find its final stellar homes around these small suns. It might learn to collect weak light, shield against flares, build within planetary systems, and persist through spans that dwarf all earlier history. But at last the red dwarf changes, its output shifts, its fusion slows towards silence, its remnant cools. The future then becomes a question not of finding another ordinary star, but of surviving without one, using stored energy, artificial power, compact remnants, or physics beyond present engineering. The red dwarf offers the longest path lit by ordinary starlight, but it is still a path with an ending. That ending is not tragic in the usual sense. It is simply proportion. The universe gives small stars more time than bright ones. It lets them remain while giants vanish, while sun-like stars become remnants, while galaxies age into dimmer structures. It allows them to be the last steady furnaces of hydrogen fusion, the final common lights in a fading stellar age. Then even they pass from star to ember to darkness. Their story stretches so far that the current universe seems young, and still it remains finite. The last living stars do not defeat time. They reveal its depth. A red dwarf begins almost hidden, burns almost silently, and may outlast nearly every familiar source of light. Its final transformation into a white dwarf, and eventually into a black dwarf, is the quiet closing of one of nature's longest processes. In that closing, the faintest stars become the last witnesses, not because they shine the brightest, but because they keep shining after almost everything brighter has gone. When the lights fade, the universe does not become dark all at once. Darkness arrives unevenly, after the brightest fires spend themselves and the supply of new stars grows thin. In the present age, galaxies shine with many kinds of light. Massive stars pour out blue radiation and die quickly. Sun-like stars burn with steadier warmth, then swell and shed their outer layers. White dwarfs cool slowly among the remains. Young clusters glitter inside dusty regions where stars are still being born. But this bright variety depends on fuel that is not renewed forever. Galaxies need cold gas to make new stars, and over immense time that gas is locked into stars, blown away, heated, or left too diffuse to collapse easily. Star formation declines. The cosmic sky becomes less crowded with new suns. The short-lived stars vanish from the living population. The universe enters a longer, dimmer age, and in that age the red dwarfs remain. They do not save the universe from darkness. They delay it with patience beyond measure. Their faint red light becomes the last ordinary starlight, not because it is strong, but because it lasts. This future is difficult to picture because the current universe is still full of activity. Galaxies continue to form stars in many places. Planets orbit countless suns. Stellar deaths enrich space. Collisions and mergers reshape large structures. Yet beneath the present motion, a slow trend points forward. The brightest stars are always temporary. They spend their fuel in spectacular amounts and vanish long before smaller stars change much at all. A red dwarf born in the early universe may survive through the entire main life of the Sun, through the deaths of countless generations of larger stars, and into an era when the night between galaxies is colder and emptier than anything familiar now. In that distant time, a galaxy may no longer look like a spiral full of bright knots and blue star-forming regions. It may look older, redder, quieter, its remaining glow carried by low-mass stars and cooling remnants. Red dwarfs become the lingering pulse of ordinary fusion in a universe that has largely stopped making new suns. Their light may also mark the last natural havens for life, if any life persists. Habitable worlds around red dwarfs are not guaranteed. Many may have lost their atmospheres, dried out, frozen, or become hostile through tidal stress and stellar activity. But some may survive, and some may be supported by intelligence rather than by natural climate alone. A civilization in the deep future would not choose red dwarfs because they are easy. It would choose them because they are still there. Their planetary systems may provide matter, their weak light may provide energy, their long lifetimes may provide continuity around a suitable small star. Living systems, machines, archives, or descendants of intelligence could endure through spans that make Earth seem young. The red dwarf becomes a hearth in the late universe, small and difficult, but still capable of warming something that wants to continue. Even then, the setting would be strange. The sky around such a future world or habitat might contain few bright stars. Many once luminous suns would be white dwarfs, dim remnants, or dark bodies. Giant stars would be rare or absent unless star formation continued in isolated pockets. The Milky Way itself would have changed through mergers and gravitational encounters. Stellar neighborhoods would drift. Orbits would be altered over great stretches of time. The familiar richness of a young star-forming galaxy would give way to a quieter architecture of survivors. Red dwarfs would not blaze in that darkness. They would glow with restraint, casting close warmth on tight orbits and leaving most of space cold. To any life that depends on them, their weakness would be intimate rather than grand. A red dwarf does not fill a vast planetary system with sunlight the way the sun does. It creates small zones of possibility near itself, pockets of warmth in a wide dark. The phrase last star sounds final, but the ending of starlight is more like an extremely long tapering. Different red dwarfs have different masses, and their lifetimes vary. The more massive ones exhaust themselves sooner. The smallest ones persist longest, using hydrogen with the deepest economy. As the ages pass, the population of living stars shifts toward ever smaller survivors. The last true star is likely to be a tiny red dwarf near the lower boundary of sustained fusion, one that has spent almost all of cosmic history shining too faintly to impress the eye. It may have no living planet. It may drift alone or with cold companions. It may be part of a galaxy that has faded into a loose collection of remnants. Yet as long as hydrogen fusion continues in its interior, it remains a star, one of the final places where the old process still operates. As gravity compresses, nuclei fuse, energy escapes, and space receives light. When the last such red dwarf approaches its end, there is no cosmic ceremony. The star changes slowly, perhaps growing hotter for a time, perhaps passing through the predicted blue dwarf stage that the present universe is too young to contain. Its hydrogen supply finally becomes insufficient for continued fusion. It leaves behind a white dwarf, dense and hot at first, then cooler with every passing age. That remnant radiates stored heat into a universe already filled with other fading remains. Eventually, after still longer spans, even white dwarfs are expected to become black dwarfs, cold, dense bodies that no longer shine. The lights do not switch off in a single moment. They sink below detectability, one remnant after another, until ordinary starlight becomes a memory written only in structure, gravity, and cooled matter. The red dwarf's final gift is not eternity, but postponement on the larger scale nature allows for normal stars. It extends the era in which planets can receive stellar warmth. It gives chemistry more time. It gives any surviving intelligence a longer horizon. It gives the universe a slow twilight rather than a sudden end to luminous life. But it cannot stop the direction of change. Fuel is finite. Expansion continues. Matter cools. Systems drift toward states where usable energy is harder to gather. Red dwarfs are the longest candles, not the defeat of night. Their meaning comes from the contrast between modest appearance and immense duration. What is nearly invisible now may become the final visible thing. What is ignored by the unaided eye may carry the last chapter of stars. In the present, red dwarfs surround the sun in quiet numbers. They host planets that may be barren, hostile, hidden, or alive. They flare, darken, mix their interiors, and burn with a thrift that makes them difficult and precious at the same time. They connect the search for alien life with the far future of the cosmos. They force astronomy to look beyond brilliance and ask what persists. They reveal that the universe is not only shaped by the largest explosions or the brightest suns, it is also shaped by small, steady engines, by faint bodies that gather just enough mass to ignite, by worlds that orbit close in red twilight, and by time scales so long that no red dwarf has yet reached old age. Their story begins as a correction to the visible sky and ends as a meditation on the final sky. The stars most easily seen are not the stars most likely to remain. The final universe may not belong to giants, supernovae, or golden suns, but to dim red objects that spent their lives almost hidden. When the brighter lights have faded, a red dwarf may still hold a little hydrogen, still carry fusion in its core, still warm a narrow region of space around it. Perhaps there is a world with air, perhaps there is only stone, perhaps there is a constructed shelter, an old archive, a patient machine, or nothing at all. The science cannot promise inhabitants, only possibility, but the star itself is enough to change the feeling of the future. The universe does not rush into silence. It lingers, and its lingering is red at last. When the final red dwarf cools into a remnant, and the last ordinary fusion light disappears, the cosmos becomes a place of dark objects and faint traces, of gravity without flame, of histories no longer illuminated by stars. Yet even that darkness is not empty of meaning. It contains everything that once happened under starlight, the making of elements, the shaping of planets, and perhaps the long migrations of minds that learn to follow the smallest suns. Red dwarfs are the quiet witnesses to that whole arc. They are born in darkness, live in faintness, and carry light farther than any brighter star can. When the lights fade, their lesson remains simple and vast. In the universe, endurance often arrives softly, and the last glow may come from the smallest flame. Long after the last bright constellations have changed beyond recognition, the thought of red dwarfs remains quietly steady. They are not the stars that first taught humanity to name the sky, yet they may be the stars that hold the sky together in its longest age. Their light is small, their warmth is close, and their promise is never simple. Around them, planets may freeze, flare, dry, endure, or shelter oceans beneath dim horizons. Some may remain lifeless stones, some may carry only chemistry. Some, in rare and patient circumstances, may become places where life continues under a red sun. The universe gives no certain answer, only a vast field of possibilities shaped by physics, time, and chance. Red dwarfs make that field larger. They show that importance does not always arrive with brightness, and that the quietest things may last the longest. In their slow fusion, there is a lesson written across trillions of years. Energy can be spent gently and still matter deeply. The sun gives Earth a luminous beginning, but the smallest stars point toward a future where survival, if it exists, may depend on patience rather than abundance. Their glow may one day be the last ordinary warmth in a universe of cooled remnants and drifting worlds. Until then, they continue almost unseen, carrying hydrogen into helium, holding close planets in reddish light, and extending the age of stars far beyond the present moment. The story remains open because the red dwarfs themselves remain young. Their final chapters belong to a cosmos not yet old enough to read them. For now, they burn softly in the dark, small flames with enormous futures, reminding the universe that the last light may not be grand, only faithful.